This is a tutorial for the uniform motion end of unit question. Please remember that to get the most out of this, you need to pause the video and actually go through a lot of these steps yourself first. Physics isn't a spectator sport. You can't just watch me do the problem. That won't help you very much. So anyways, let's go ahead and get started. The first thing that we need to do is figure out what this question, which has a lot of different numbers and multiple objects and a lot of context, is actually asking. So please go ahead, pause the video, and try to translate this question into a very simple question that we can use our physics tools to answer. This question is really asking us to figure out how fast does the second sub need to travel so that it gets to the exact same point at the middle as the first sub at the same instant in time. That's what we're trying to figure out. And to do that, the first thing that we need to know is what type of physics will help us solve this question. And so far we've only seen one type, it's kinematics. And kinematics is the study of motion. Its purpose is to describe what happens when things move. And even within kinematics, there's kind of two major models that we have. There's a uniform motion model and a non-uniform motion model. This one is a little tricky because there are different velocities that the subs travel at in this problem, but they don't speed up or slow down. So they just travel at one specific velocity, say 30 kilometers per hour for a time, and then we're assuming that they instantaneously change to 20 kilometers per hour. And so in this case, it makes more sense to say this is a uniform motion type question. Now, the next thing that we need to do to understand this situation is we need a picture. And on your picture, you should make sure that you include a coordinate axis, and please label either on your picture or to the right the things that we know and the things that we don't. That's going to help us to understand the question, which ultimately allows us to answer it. So please go ahead, pause your video, and draw your picture. Okay, first thing that I'm going to do is put my origin smack dab in the middle of the two subs where they meet. I'm going to say the right is going to be positive, and the first submarine, I'm going to draw it in red on the right side, and then the second one over here, you can see that they should be equally far from the center where they meet. We also know that the first submarine takes 4 motions, and each one it goes 500 kilometers. So overall it had to travel 2,000 kilometers, and since the other blue one is equally far at the beginning, it has to go that far as well. Now the next thing I want to do is just kind of show on my diagram that the red sub goes in 4 different motions. Each one has a different constant velocity, and here's the 4 parts. Okay, and we can also identify, we know several of the variables are given in this problem. The first sub's velocity at the start, so the sub 1 velocity is 20 kilometers per hour, and its second velocity is 40. And then it goes the next 530 kilometers per hour, and finally 50 kilometers per hour. And I also think that it's worth noting that all of these are for 500 kilometers. Finally, we want to know the velocity of the blue sub, and we know that it has to reach the center in the same time. Okay, so we got a picture. We know what the situation looks like. We know where our origin is, which way is positive. We've identified what we know and what we don't. The next thing that you want to do to further your understanding of this question is start drawing physical representations. And so what we mean by that is graphical descriptions, motion diagrams, or strobe diagrams. You don't have to do force diagrams yet. We haven't quite got there. But please go ahead, draw those, and do make them quantitative, so use numbers. Overall, our objective in this process is to start from very general and to work our way to more and more specific. So you can see that the graphical representation, for example, is more specific than the pictorial representation. So, okay, go ahead, pause and draw what you think, and then I'll show you mine in a sec. Okay, I'm going to go ahead and draw the motion map first. And for the red sub, it goes the first 500 kilometers relatively slowly, so that will take a long time. Then it does the next 500 kilometers twice as fast, so only half the time. Oops. And then the next chunk is 30 kilometers per hour, so somewhere in between. And then finally, it does the last 500 kilometers at 50 kilometers per hour, so that should happen relatively quickly. And so let's go ahead and label this was the start of that motion, and let's put the origin at the place that the red one ends. So just to make this clear, the first motion is going at 20 kilometers per hour, and that's this piece, the first 500. Then does the next one. And the third piece. And last but not least, final 500 is over here. Okay, so now that we know the sort of complicated sub, let's try to think about the blue one. First off, we know that it should start 2,000 meters in the opposite direction, so it should be approximately as far away, so it looks like about here. We also know that it takes the same amount of time to get to the center, so it should have the same number of dots. Looks like 1, 2, 3, 4, 5, 6. And this one travels the same speed the whole time, so these arrows should be the same. And this was the starting point. Okay, the other thing that we need is quantitative position versus time graph and velocity versus time graphs. Since the red sub, well, since both of the subs start out 2,000 kilometers away from the origin, let's go ahead and put those in. So we know that the red stub starts to the right of the origin in the positive part, and so it starts up here. Its first motion is relatively slow, so it takes a long time to go about a quarter of the way in, and then it goes another quarter, twice the speed, so about half the time, and then it goes a bit slower but relatively quickly, and then it does the last quarter very, very fast at 50 kilometers per hour. And then we know the blue one, of course, starts to the left of the origin, and it goes at just one constant speed. In the same amount of time, it reaches the same position at the origin. Now, next up is the velocity versus time graph. And the first thing we want to think about here is if these lines should be on the top or the bottom. And so if we do the red one first, it's moving to the left the whole time, so it should have negative velocities. And the first motion is relatively long and slow. Then it doubles its speed, so that should happen about half the time. And then it goes at somewhere, this is a little unclear, let's try that again. Okay, so it's going at negative 20 kilometers per hour for a bit, then it doubles it to 40, but only half the time, and then it goes at 30 for some amount of time, and then relatively quickly it does the final 500 kilometers per hour. Sorry, 50 kilometers per hour, but it travels the same 500 kilometers. Now we know the blue one is traveling in the opposite direction. It's also traveling at some speed that should be more than 20 but less than 50 kilometers per hour. So I'm just going to say right there, we know that it should take the same amount of time. And so at this point we have quantitative position versus time graph, velocity versus time graph, and the motion map. So what you want to think about next is how can you either use algebra or these graphs, and it can be done either way, to figure out actually solve the question of how fast should the blue sub be going so that it gets to the same place at the same time. So please pause and think about it. One thing I should have done in the last one was label my velocity versus time graph. So let's go ahead and put in those numbers. It's kind of small, but at least there's a few. So like I said before, there's different ways that you go about solving this question. I believe that the easiest way is the graphical solution. So I'm just going to go ahead and redraw my velocity versus time graph a little bigger to make it more clear. So let's see, 10, 20. And like we said before, goes for a long time at 20, about half the time at 40, somewhere in between at 30, and then relative short amount of time in the last part. So if you remember, there's a way that you can figure out displacement from a velocity versus time graph, and that's the area. So if, for example, if we knew in this first part that we were going at minus 20 kilometers per hour, and we did it, for example, for 1 hour, then of course you would have gone 20 kilometers. In this case, it was stated, we know from before, that each of these displacements are 500 kilometers. So I'm going to go ahead and fill that in. So that area is 500. So is this one. And if I draw this well, all of these boxes would look like they're the same area, which they kind of do. And by the same token, for the blue sub, we don't know how fast it's going right now, but we know that it has to travel the same amount of time. And we know that the area of this one, I'm going to write up here, is 2,000 kilometers is the full trip that it goes. So if we can figure out the time that it took the red one to complete its full motion, then it's going to be relatively easy to figure out how fast the blue one needs to go to get there at that same amount of time. And so to figure out the times is not too hard. So since it's going at, in the first part, minus 20 kilometers per hour, and we know that it has to go 500 kilometers. We can just figure out how long does it take to go 500 kilometers at 20 kilometers per hour, and that's 25 hours. So let's put that in here. In the next part, we know that it does the same 500 kilometers, but it does it at 40 kilometers per hour, so it'd be half the time, and so that's another 12.5 hours, which added to 25 is 37.5 hours total. And then in the third step of the trip, where the sub is going at 30 kilometers per hour, once again we'll do, in all these cases I'm just doing the velocity is equal to the displacement over the time, and I've rearranged so that time is equal to displacement over velocity. So anyways, it's 500 over 30 is 16.6, and if we add that to the 37.5 that we already have, up to the third motion will take about 54.1 hours. And then, of course, to go 500 kilometers at 50 kilometers per hour will take another 10 hours, which brings us to a grand total of 64.1 hours. And so this is really useful because now we know that the blue trip had to take 64.1 hours too, because it started at the same time and it ends at the same time. And so if you want to go 2,000 kilometers in 64.1 hours, you better be going 31.2 kilometers per hour. Okay. One thing to realize, though, is that we're not really done just yet. Even though we have a number, there's other things that we need to do to be confident that this is actually what we were looking for and we really did understand this problem. And so you can see in the next step, you need to check things like the sign. So in this case, it was just a speed. It didn't have direction, but if it did, that's something you should think about. Is the magnitude reasonable? Is this a value that we might have expected? Is it kind of in the ballpark, or is it crazy? Did we include units, and did we box it? So please go ahead, pause your video, and check to see if your answer has taken care of all those important details. Okay. Kind of take a step back and think about if this is a reasonable answer or not. First, the question asks for the magnitude of the velocity or the speed, so that doesn't have a direction, so we don't have to worry about that in this case. The magnitude of 31.2 kilometers per hour also seems pretty reasonable, since it's faster than the slowest. The red sub at minus 20 kilometers per hour is going, and it's slower than the fastest at minus 50, so it seems reasonable to be in that range. We have a unit on it, and the answer is box, so it looks like we're in good shape. So let's kind of zoom out and take a look at everything we did. I hope you notice a couple things about this process. First, at no point did we just start searching for algebraic equations and start indiscriminately throwing numbers into them. That's not a good strategy, especially when you have a lot of different velocities and a lot of context like this question has. Second, each of these individual steps, like when we figured out what the question was asking and we thought about what type of physics would be helpful and drew a picture and figured out what we knew and what we didn't, and started working on the graphs and the physical representations, all those steps are by themselves very simple, and I don't see any reason why you couldn't do those steps even if you didn't really completely know how to do the problem, or you didn't know how to get to the answer. But once you have them, it makes it a lot easier to do the fifth step where you're figuring out what is the actual answer to the question. So it's, in my view, very important that you make sure that you understand the question before you try to get an answer right away. This process kind of mirrors how experts do physics problems, and I hope that you use it as we go through physics this year. I think that it will serve you well. If you have questions, please let me know. Otherwise, that's it.